Hi all, and welcome to this 10 days workshop on reinforcement learning brought to you by Innomatics Research Labs that starts on 17th of December at 7 p.m. In this brief talk, let's quickly define what reinforcement learning is. So you might have come across this paradigm of machine learning where you might have seen both supervised learning techniques as well as unsupervised learning techniques. In supervised learning techniques, you learn from examples. You're provided some input-output pairs. Say for example, you're given a bunch of data as in the form of images and your objective is to learn to predict as two classes, say cats and dogs. That's a supervised learning setting. In unsupervised learning setting, you are not provided with explicit output and your objective is to find some patterns in the data. You might have seen the algorithm of clustering where your objective is to classify or group this entire data into clusters or into small groups. But there is also a third paradigm in machine learning called reinforcement learning, where the objective of the agent is to learn to behave optimally from a reward and punishment setting. Now consider the task of learning to ride a bicycle. This was neither an unsupervised learning setting nor a supervised learning setting. You were not trying to find some patterns in the data, right? So it's not an unsupervised learning setting. Also, you were not trying to calculate what amount of force leads you to move forward in the road. So this was not even a supervised learning setting. Rather, it was a reward and punishment based setting. What do I mean by this? So while trying to ride a bicycle, if you fall down, then you get a punishment. And if you don't fall down and you keep on moving, then you get a reward. And then your objective was to learn to behave optimally, that is, to ride a bicycle in such a reward and punishment based setting. Let's look at this in somewhat more detail in here. So you have some environment. In this case, the environment is the entire road. And you as an agent, you are currently at some state ST. Here ST in your case is when you are standing on the road. Then you take some action AT. You either push your brake or push your pedal. And then the environment takes you to a new state. You might fall down or keep on moving on the road. At the same time, the environment also spits out a reward RT plus 1. If you fall down, then it gives you a negative reward. If you do not fall down and keep on moving, then it gives you a positive reward. So this is the entire framework in which reinforcement learning agents learn. So now next, why even study reinforcement learning? The first reason obviously is that it finds many applications in the industries. I've listed a few of these applications. The first one is that of a recommendation system. Recommendation systems are systems where it provides you with some recommendation. For example, Netflix might provide you with movie recommendations, and such systems can be modeled as reinforcement learning agents. We'll discuss recommendation systems in great detail as a case study in one of the sessions. Next, chatbots. You might have seen chatbots in a natural language processing course or deep learning course. But chatbots on the other hand can also be modeled as reinforcement learning agents, and again we are going to spend a single session as a case study on chatbots. The third one where reinforcement learning is heavily used is the robotics industry. Fourth one is self-driving cars, where the optimal goal of any self-driving car is to remain in the road and not hit pedestrians as well as follow the traffic rules. And again, self-driving cars can be modeled as reinforcement learning agents, and such mechanisms can be used to train these cars. The fifth one is that of stock trading, where you're selling, buying, or doing nothing with a trade. So at a given day, you can either sell a trade, buy a new trade, or do nothing. These three different things can be modeled as three different actions that you as a reinforcement learning agent can do. And therefore, stock trading can also be modeled as a reinforcement learning framework. Again, stock trading is going to be a case study in this course, and we are going to spend an entire session on modeling stock trading as a reinforcement learning agent. The second more broad reason is that reinforcement learning is currently one of the hope towards general artificial intelligence. You might have come across this term. The goal of general artificial intelligence is to create artificial agents that are as good as human beings in all terms. So they can learn as efficiently as us and behave in the optimal way like human beings do. And currently reinforcement learning is seen as a framework that might lead us to general artificial intelligence. Now let's briefly discuss what are the learning outcomes of this particular RL workshop. The first one is you'll have a comprehensive understanding of this entire RL framework. Second, you will understand how to model your problem, the specific problem that you are facing in industry, how to model that into an RL setting. Third, you'll have an in-depth understanding of some of the major algorithms in RL, and you'll be able to select whichever algorithm suits best for your problem. Fourth, knowledge of the most famous RL API called the OpenAI Gym. We are going to spend many hands-on sessions implementing various algorithms on OpenAI Gym environments. Fifth one is the ability to code all the major RL algorithms in Python. So we are going to see 3 case studies: chatbots using RL, recommendation systems using RL, and stock tradings using RL. Along with this, we are going to have multiple hands-on sessions implementing various algorithms on many environments in the OpenAI Gym framework. Now let's come to the brief syllabus of this 10 days workshop. So each of the session is going to have 2 parts. Each part would be 1 hour long, and you'll have a break of about 10 to 15 minutes between these 2 parts. In the first session, we're going to introduce you to this RL framework. We're going to discuss the basic mathematical framework called Markov decision process in great detail. Then we'll take an example of robot navigation and model this as a Markov decision process. So you'll understand how to translate your particular problem into an RL framework through this Markov decision process. We'll also define what the goal of an agent is in reinforcement learning. In part 2, we'll have a hands-on session on OpenAI Gym environment. We'll specifically look at an environment called card pole, where you have a card and a pole, and your objective is to balance this pole on top of this card by moving the card either left or right. In session 2, we're going to introduce you to temporal difference algorithms. In part 1, we'll discuss 2 algorithms, TD0 and Q-learning. These are the 2 most famous algorithms in RL. Then we'll briefly introduce you to deep learning, and in part 2, we're going to combine reinforcement learning and deep learning to form this algorithm called deep Q networks. This was the reason for the current boom in deep reinforcement learning. We are going to implement this DQN algorithm on this game of Pong. So here you have 2 players, and the objective of each player is to hit this ball and pass this on to the other player. If the other player misses the ball, then you get an increase in your score. We'll implement DQN to solve this particular problem of playing a game of Pong. In session 3, we are going to do a case study on stock trading. So in part 1, we'll introduce you to the stock trading in the RL setting. How do I formalize this entire stock trading framework using RL? And then in part 2, we are going to have a hands-on session using Python of this entire stock trading using RL. In session 4, we are going to introduce you to another class of popular reinforcement learning algorithms called policy gradient methods. In part 1, we'll discuss the basic principle behind these class of algorithms, and in second point, we'll introduce you to another algorithm in the policy gradient method called reinforcement algorithm. In part 2, we'll discuss this policy gradient methods in the specific environment of card pole and implement it using Python. In session 5, we are going to introduce another family of algorithms in RL called actor-critic methods. Here you have 2 components, an actor and a critic. The actor takes some action and the critic tells whether that particular action was a good action or not. Based on the feedback, the actor changes itself. So in part 1, we'll discuss all these basics of actor-critic methods and also introduce you to a specific actor-critic algorithm called advantage actor-critic, A2C. In part 2, we are going to implement this A2C algorithm on an environment in OpenAI Gym called Lunar Lander, where your objective is to land a particular spacecraft on Moon. In session 6, we are going to have our second case study on chatbots. So in part 1, we'll discuss in great detail some basics of NLP and recurrent neural networks, RNNs. and we'll also discuss NLP based chatbots. In part 2, we're going to show you how to introduce RL into chatbots and have a hands-on session on this. In session 7, we're going to move to more complicated environments. Here we are going to look at continuous action spaces. So recall that until now, the actions that we were taking were discrete. And what do I mean by discrete? You had a fixed number of choices. You could either move left or move right. Okay? But you could also be in a continuous action space environment. In part 1, we'll introduce you to two algorithms, deterministic policy gradient called DPG and the deep learning version of this algorithm called deep deterministic policy gradient called DDPG. In part 2, we are going to implement this DPG algorithm using Python. In session 8, we are going to introduce another class of RL algorithms called trust region methods. In part 1, we are going to introduce you to two specific algorithms in this class called proximal policy optimization PPO and trust region policy optimization TRPO. In part 2, we are going to implement TRPO to solve this problem of a bipedal robot walker. This is the bipedal robot walker from OpenAI Gym environment, where you have a bipedal robot walker, and the objective of this walker is to learn to walk properly so that without falling down it can reach a certain goal. Session 9 is again going to be a hands-on session, a case study on recommendation system. So in part 1, we'll formulate a recommender system using RL. So if you consider the example of Netflix as a recommender system, Netflix gives you some choices of movies to watch. If you click a particular movie, then Netflix gets a positive reward. If you do not click that particular movie, it gets a negative reward. And in this framework, it has to learn to behave optimally. That is, it has to learn to provide you with the best choices. So we are going to formulate this recommender system using RL, and in part 2, we are going to code up an entire recommendation system using Python. In the last session, session 10, we are going to introduce you to the most famous application of RL to this date, the game of Go and the agent Alphago. So in part 1, we'll discuss this game of Go, where there are two players, white and black. I, as the white player, my objective is to fill this entire board with whites, and my opponent's objective is to fill this entire board with blacks. This is indeed a very difficult game. It's much more difficult than the game of chess, and Alphago was the architecture, a deep reinforcement learning based architecture that did beat the world champion of Go. So we are going to discuss this Alphago architecture in much detail in part 1, and in part 2, we are going to code some of the basic building blocks in Alphago. Before concluding, let's quickly discuss what are the prerequisites that we expect from you. First, you need to know some basic algorithms from machine learning and also from deep learning. In deep learning, if you are exposed to convolutional neural networks, CNNs, and recurrent neural networks, RNNs, then it would suffice for the entire course. If you have taken the courses some time back and you do not remember, it's okay. We are going to revisit these architectures, but not in much detail. The third prerequisite is exposure to programming in Python, because this entire course, all the hands-on session would be in Python. So we require you to have basic understanding of Python programming. So that's it. I'm really super excited about this workshop and hope to see you all on 17th of December at 7 p.m.